All right, so let's start talking about some acid-base chemistry. Towards the end of our last class, we talked a little bit about the differences, kind of like with our nomenclature. I want to do a quick reminder there. When we're thinking about acid bases, we're going to see a lot of stuff with the letter H referring to hydrogen. However, depending on the amount of electrons there are, that name can change. Hydrogen, specifically a hydrogen atom, is going to be H, which carries a single electron, kind of like that Lewis structure drawn there in the top middle of our page here. If we go and we remove that electron and we just have that hydrogen ion, we'll call that a proton, because in the nucleus it is just a proton and there's no electrons whizzing around. So that's kind of like the simplest like subatomic unit we have. And then if we add an extra electron where that H has a lone pair and therefore a negative charge, we call that a hydride. And this general kind of like description of what we're thinking about with acid base kind of is going to just build on stuff that we talked about back in general chemistry, where we are looking at a reaction where that hydrogen, specifically that proton, is going to be moving from an acid to a base. And in our Lowry-Bronsted definition, the proton donor, the thing that has it and loses it, is going to be our acid, and then the acceptor is going to be our base. If we kind of think about a little bit of tracking here, we have a generic reaction where we have HA, which refers to our acid, plus our B, which would refer to our base. We show an equilibrium arrow because this can go back and forth, going to our conjugate base being our A minus, and our conjugate acid being the protonated version of our base. When we think about our electrons and where they are in O, the electrons that exist here in the bond between H and A end up being the lone pair electrons on our A, and then the lone pair electrons, which we'll go ahead and show in green here, are going to be the electrons here inside of this bond. And one of the things that we're going to get to towards the end of this video is showing a mechanism or an arrow pushing set of arrows, which are going to show how these electrons move and where they're involved in terms of our reaction. Now, before we get there, let's go ahead and think about just our first kind of generic acid. And let's think about NH3. So NH3, if we draw, I guess this is kind of a little bit more Kekule than Lewis because I don't have the appropriate geometry. I don't show a trigonal pyramidal view here. But if I look at NH3, there are two possibilities that can happen. This can either accept a proton or it can lose a proton. It can donate a proton. And that can change whether it's an acid or a base. So if we, let's say, go ahead and look at this side here, let's do one where you do minus and H plus, and then on the other side, we'll do plus and H plus. If we lose a proton, we would get a conjugate base that would carry a negative charge, where if we gained a proton, we would form an ion, which would be our ammonium ion. This would be the difference of if this lone pair, and if we kind of define here, if this ammonia acts as a base, it would use these electrons that we have here in this lone pair to get another hydrogen, specifically just a proton, and form our ammonium. We're going to call this our conjugate acid, because in the reverse reaction, this would lose an H. And then if it was an acid and we lose one of our protons, we would have two sets of lone pairs now and a negative charge. So there are some species, so for example here in ammonia, that can be either acidic or basic. And what's going to really matter is going to be what is the other component. In all of our acid-base reactions, we're going to have two different components, one that's going to be donor and one that's going to be an acceptor. So depending on the identity of like the second component, you might get an acid or a base. In this case, for ammonia, most of the time it's actually going to serve as a base based on its general properties. And in a future video, we're actually going to kind of get a series of values, which is going to be called pKa, that can generally see that, those trends between the strength. Now, one of our big questions is going to be, how do we actually get these reactions to occur? what is the actual movement of electrons? And that process of how I can go from ammonia and immediately draw like what the product is because of the fact that I've already kind of thought about the mechanism and thinking about how electrons move. And that's going to be something that we're going to get a bunch of practice, not only for acid-base, but for every single type of reaction we do in organic chemistry. So in general, a mechanism is going to be a series of curved arrows, similar to what we see when we do resonance structures. However, rather than just showing those electrons moving within kind of a delocalized section of your molecule, here we're actually seeing an actual reaction happening where bonds are breaking and bonds are forming. And an arrow is going to show the movement of electrons. And just like resonance, we're going to start from the source of electrons and then show kind of where they're going. One thing that students will often kind of struggle with is thinking that we want to show the movement of atoms, but we do not. A mechanism is purely showing the movement of electrons. And it's kind of our bookkeeping approach, where we're seeing where do electrons go from our starting materials to our products. And if we kind of think of a few terms that we've used back when we were talking about resonance, we're going to have a sink and a source. Our source is going to be where our arrow starts, and that's going to be where our electrons are. So in our acid-base chemistry, our source of our electrons is going to be the base. That base is going to often have a lone pair, often with a negative charge. If you think of like a hydroxide ion, which would be an HO minus, that's going to be kind of a big tell that we're looking at a base. That's going to be the source, and then the sink is going to be where those arrows go. So in this case, the electrons in this lone pair want to make a bond with our proton. And we want to ultimately make this BH. So the way in which we show this is we're showing the electrons from that base going towards that hydrogen. And that arrow right there is showing the process of making a bond. And anytime we have arrows that are coming from a source that are going to be going towards our sink, that's going to be the process of making a bond. Now, we know that hydrogen only wants one bond. So if we now have a new bond between our B and our H, that hydrogen would be overloaded. It would have two bonds. That would be a violation of the octet. So there's going to be kind of a consequence, much like when we're thinking of resonance, when you had like lone pair to double bond to lone pair. Here, you're also going to have that same idea, but we are actually physically breaking a bond because we're doing a reaction. And here, we are going to show the electrons that exist. Let's go and change our color. Here, in our HA, those are going to break and go to our A minus. So this is our breaking bond. And those are going to end up as a lone pair on our conjugate base. So for our acid-base chemistry, we will almost always have exactly two arrows, one of them being from our base to our acid to abstract our proton. Abstract just means take off. And then a second arrow, which is going to be from our arrow or from our bond itself, which are going to be breaking to give us a lone pair. And that same process we're going to see kind of again and again and again. And we're always going to have these two arrows. It is always going to be really important that we actually draw that bond between whatever is connected to our proton to show that actual physical bond. Because if you don't show that bond, you can't have that second arrow. And at that point, your reaction is going to be wrong. So let's go ahead and do an example kind of like from above. And let's go ahead and just consider that ammonia that we talked about in our last example. So here we have ammonia, and let's go ahead and react this with water. Now, if I look here, both water and ammonia have some H's that we would be able to abstract as a proton, and they have some lone pairs. So realistically, based on your knowledge now, we could say either of these could be an acid or a base. Eventually, through our pKa tables, which we'll get to in, I think, 2 or 3 videos, we are going to learn that our ammonia is going to be a stronger base, and therefore our water is going to be our acid. So if we wanted to show this mechanism or this movement of electrons to make bonds and break bonds, we're going to start with our source, which is going to be our base. And this is going to be the lone pair of electrons on our nitrogen. And these are going to come and grab our H. And here we want to abstract just our proton. We don't want to actually take the electrons. So we need to show where those electrons are going. And those electrons are going to go to our oxygen. And there's our two sets of arrows, lone pair to our H, and then bond to our atom. And if we draw the product now, I'm going to draw everything the same for my ammonia, except I'm now going to do a new bond instead of a lone pair, because that's what that arrow showed. That first blue arrow is showing the making of a bond to a hydrogen. This now gives me my conjugate acid. This is our conjugate pair between ammonia and ammonium, the ion. And then my product, which is now going to be our water that's deprotonated. So it's going to have 3 lone pairs and a minus charge. You'll see we actually are net neutral. We have no charges in our kind of reactant side in our product. We have 1 plus and 1 minus. So we have a conservation of charge there. And this will be kind of how we kind of show our movement of our electrons. So we start from our base, do an arrow towards that H, and then break the bond that H originally was connected to make a lone pair. And this is going to be something that we're going to show again and again and again for almost every single type of reaction that we'll do in organic chemistry. And this is our basics of a mechanism. Our kind of curved arrow notation showing our making and our breaking of our bonds. So we'll go and stop here for this video. And in our next one, we're just going to get a bunch of practice kind of thinking about more drawing of arrows and seeing some acid-base stuff.